thank you very much for the invitation to talk. I'm going to talk a bit about some of the work we're doing at CSIRO. And this is kind of not so much a service provision kind of service that we run, but it's taking lots of the aspects of the things that we've heard about this morning and using them to understand how we can really understand mineral systems for exploration and further downstream. And that will combine our new Drill Core Lab facility with the Maya Mapper instrument, which is a CSIRO developed instrument. And then Sam, who follows on after me, will give a case study of how we've applied that to an exploration context. So I called this detail and context because, as we saw this morning, when you get nice micro scale information over large areas, you can really start to pull apart what's going on in your systems. So the outline, I'll just talk briefly about the Drill Core laboratory and combining some of these techniques, and then how we're going about that. So talk about a little bit about machine learning, because everybody does, and data Mosaic, which is an application of that to produce some nice consistently logged data. And then most of the talk will be on the Maya Mapper, which is this instrument that kind of nicely fills in the gap between these core scale applications we've heard about this morning and the true microanalysis that's coming. So we heard about a whole range of new technologies this morning that are all doing fabulous things and producing new data sets. And many of these, as was pointed out, actually reproduce objectively with numerical data existing practices. So we can take, for example, our downhole XRF data, and we can use that to assist in logging and use that to log. I think one of the things we have to think about, and this is certainly where we're heading, is what happens if we have multiple of these streams of data, like, for example, with the geotech logger that collects a whole bunch of different data sets. What extra value can we get out of those? And these are complementary techniques, so it's not A against B. It's how can they kind of work together, and what's the most appropriate combination or technique for your application. And you can see here where we've got three holes, and we've got two that have spectral data from the high logger, which is 1D spectral data, and Mineralize XRF. And when we were looking at this, we noticed that in the high logger we have this enrichment in white mica, and in the XRF we have this enrichment in copper. And with these two data sets together, we actually realize that what we're seeing here is stripping of the copper out from the underlying volcanics, and it's going into the overlying sediments. And this is manifested as white mica alteration. So we're really able to understand these systems more completely just by using these two data sets. So the Drill Core Lab that we've been putting together at CSIRO, which is now almost nearly finished. The lab is built. We're just in the process of putting the instruments in, and some of you will see the space tomorrow. Combines the Mineralize, the core scan, a high logger, and a geotech multi-sensor core logger as well. So we're putting these together to bring them together in a research environment, and hopefully produce workflows and solve problems for industry using multiple of these different sensors. But how are we going to go about that? So one approach we've taken in the past with multiple sets of data is a machine learning approach. And this is just a workflow diagram showing how, when we have coincident sets of data from representative samples, so that cover the variability within our deposit or our exploration tenement, and we have some kind of characterization data, we can build this library of samples that overlap, that we have all these data types for, which is like our Rosetta Stone. It allows us to kind of see the links and translate between the different data types. We can then produce classification, and we can start to predict, given new data types, new data from new samples, predict what we might see. So we can use relatively low cost, easily acquired data to predict some of the more fancy things based on these methods. If we're satisfied with the uncertainty, because most of these methods produce an uncertainty around the measurement we get, then we're good to go. If not, we might need to expand the sample set. Just as an example, I've got some data here from Olympic Dam, which was where this project was kind of first conceived. And the inputs are just the core scan raw spectral data. So we've not done any of the beautiful interpretation that you saw earlier. We're just shoving the whole lot in. The training set for this was XRD mineralogy along with MLA mineralogy and assays and the logged lithologies. And you can see here this is the predicted lithology, and it's predicting the lithology quite nicely. And we're also predicting the assay values for a whole range of elements, some of which appear in the spectrally active minerals, others of which, like uranium, copper, don't. And we're also getting out the uncertainties. And so we're able to start predicting things even like uranium and copper, albeit with slightly kind of misaligned values at the higher end of things, even when they don't feature in any of the minerals that we're observing. Another method that we're looking at and pursuing with these numerical continuous data types, we've called data Mosaic, and it's an objective logging technique. So all of you who've logged core or dealt with core that's been logged, you'll know that the way you may log it in the morning varies from the way you may log it in the afternoon. The change of shift means different people are logging it. But here we can set up objective rules to log it not only consistently by rock type, but also at a consistent scale. And that's the important bit here. So we take our continuous numerical data. In this case, it's a whole bunch of downhole geophysics, but it could equally include the continuous XRF. We take some kind of classification plot. This is just clustering. Here, k-means clustering. And we put the data through a wavelet, continuous wavelet transform, which produces this data mosaic here. And what all this is showing us is if you had a geologist who's a splitter and logs every little teeny tiny thing, they'd log it as on the left. If they're a lumper, they'd log it as on the right. And we're able to choose a value at which we want all our data logged. This has found all the boundaries for us at whatever scale we're interested in, and we can produce consistent logging. And so this saves us time when we're modeling, because we're not trying to deal with data types and scales of logging from multiple different people at different times. We can set up the criteria, and we can relog it coarser if you're producing a resource model, and finer if you want to deal with the real intricacies of the stratigraphy, for example. So that's great, and we've heard about lots of these great tools for downhole measurements and core measurements, and we're about to hear about all these fantastic research tools which can really get into the nitty-gritty of the processes that are going on and controlling your systems. But we identified that there was a bit of a scale gap. So here we go from atomic scale data, which I'm sure will mention, right through nanoscale data, up to thin section scale, which is conventionally where a lot of the detailed studies are done. But we have to somehow choose where these thin sections come from our core tray. And even when we have centimeter data, we might only have 1 or 2 points in that thin section to kind of make that choice about where we choose it from. And so our response to this was to take some of our technology, the Maya Detector, which was developed for synchrotrons for micro XRF mapping, and bring that into the lab so that we could make it available in the research context. Now this is not, I'll explain about it first. So the Maya Detector, as I said, is developed for the high flux synchrotron facilities, which are obviously not able to be transported to site, and actually even for researchers they have a relatively restricted kind of access to these things. And so this detector has real-time processing built into the detector and the software with full spectral deconvolution. You can see here the spectrum deconvolved into quite a complex set of peaks, so we're resolving some of these peak overlap issues. And it has bespoke the GeoPixie software, which is designed for, it's a dynamic analysis method that's fundamental parameters quantification for these X-ray spectra. As I said previously, the Maya Detector was only on synchrotrons, so our challenge was, can we build a lab instrument that takes 50 centimeter lengths of core, that can map with something approaching 30 micron resolution, and gives us quantitative analysis of trace elements. Here is the solution. That's the system in Pearce that some of you will see tomorrow. And it includes a Maya detector that I talked about before. It also includes an Xray high flux liquid metal source, which I'll explain a bit more about in a minute, and uses new X-ray lenses that really allow us to achieve that micro focus. So this is the inside of that white box. There's the Maya detector itself, and behind that is the Xray Source. Now, instead of being a conventional X-ray tube where you have a solid target, which over time kind of drifts and causes beam instability, this system actually uses a liquid alloy, which it pumps through this tube inside this jacket here, and down the back. It's then hit by an electron beam and produces the X-rays. This is a commercially available source from a Swedish company, and when we were designing this instrument, we did a whole bunch of modeling around different types of potential X-ray sources that could give us a really high intensity, high flux X-ray beam. The sample you can see here, so there's Xray Source, the detector. The sample here, which is mounted vertically on the stage, it's a half piece of core cut in half and just lightly polished so that it's relatively flat. And it moves backwards and forwards in front of the X-ray beam on this stage here, kind of rastering to collect the fluorescent X-rays. And once again, it's in a backscatter geometry. So if we look, there's the sample, and if we look at a cutaway here, so we're now cutting through the detector. This is the sample over here, that's the sample face. Here's the liquid metal jet with the electron beam, hits it, generates a beam of X-rays. It actually generates one either side, so we could potentially map two samples at the same time. This is focused through the X-rays that have piezo motors to make sure it all stays in alignment and in focus. It comes through a hole in the detector, and this is the detector array here, and hits the sample, and the fluorescent X-rays are recorded in the backscatter geometry. And so we've been using this to map samples for a while now, and we found that typical kind of throughputs, if we look at 3 to 10 milliseconds per pixel, on a 50 centimeter piece of core, we've got 33 megapixel images, and these take about a day. So you can see this is not going to be on site, it's not going to be scanning all your core, but in combination with those other technologies that we've seen this morning, where we can choose where we wish to sample within that numerical data stream, we can actually subset intelligently and take the key pieces of core to this instrument, and then continue to kind of do the research and solve the problems using the more detailed microanalysis. In terms of cost, the current price is $1,500 a day. So that's kind of our nominal cost, but as we operate it, we will refine this. And our preferred mode of engagement with people is part of a research program. So we will kind of do almost like servicey type work with this, but actually I think to get most of the value out of it, you can come and engage with our researchers who can help you understand the problem a bit more, understand what the technique can deliver and the combination of techniques to deliver the best results. And we're currently working on a beautiful web interface to deliver the data so that everybody can have a look at the data back in the office. Now that was so. This image here, I'm not sure if this is going to kind of show up very well, but this is just to illustrate the difference in dwell time. So this first image. First image here is collected at 3 milliseconds per pixel, and then it's overlain by a second image which is actually collected at 12 milliseconds per pixel. So you can see there's a kind of enhancement in some of the features. We also get rid of these red bits here are artifacts that are caused by the signal being relatively low in the 3 millisecond map. And these are better resolved in the 12 millisecond map, but you can see that the 3 milliseconds actually gives us perfectly usable data that where we can identify most of the features that we see in the longer dwell time stuff. So in terms of resolution, here's an image from the Abra lead zinc silver deposit, and we tested to see what kind of resolution we could get across a boundary. So this boundary here is between quartz in black and carbonate, iron-bearing carbonate in this red color, and we're kind of resolving that boundary in the space of a pixel or so, which is giving us that, telling us that 30 micron spot is not far off. In terms of detection limits, I just pulled these data from a data set that I had. These are actually from that image that I showed you two versions of, the 3 millisecond one. And for individual pixels, as a function of the X-ray energy, so 6 and a bit is iron. Iron sits in here. So these are the transition metals. Also, gold is up around here somewhere. For a single pixel, we're looking at several hundred ppm in terms of that limit of detection. In terms of the counting statistics, if we start binning pixels together, which we can do relatively well because we've got quite a fine detailed scan, then those detection limits drop down to a few tens of ppm and less for some elements. So there are a few limitations of this particular technique. The detector can cope with energies kind of greater than 2, so we're looking at, again, sulfur and upwards. The alloy itself has indium and tin, so this wipes out a few elements that overlap with those peaks. There's molybdenum in the Maya, so trace moly's hard, although if we've got molybdenite we can see that. And the rare earths are kind of challenging if we look at the L lines, but there is some hope with some of the K lines. So I'll just show you a couple of quick examples, and then Sam will take you through a more detailed example. In terms of base metals, here's that sample again from Abra. The top is just an optical image. The bottom one shows copper in red, zinc in green, and lead in blue. And you can see there's zinc distributed throughout the sample, and we can also pick up where the copper's sitting, which of these layers it's sitting kind of in here, and the lead. So we can start looking at the relative timing of these elements. Because we've got all the elements, we can switch out which elements we put in which colors. We can also produce single element heat maps of where these things are. So if we look in a bit more detail at this area here, you can start seeing the kind of detail we're getting. And if we just consider the zinc, the zinc occurs in a number of places here. So it's within these collar-form structures. It also occurs within grains in this quartz down here, and also in the carbonate. And when we start thinking about this system, initially it was thought to be a kind of SEDEX-y layered system, and these collar-form textures would suggest that. But if I just flip back, the growth inwards of some of these carbonate phases suggests that there has been significant modification and replacement, and that actually there's been zinc mobility, because zinc here is shown in blue, iron is red, and that makes this purple. So these carbonates are actually zinc zinc-containing carbonates as well. So we can really start understanding some of the paragenesis here. The last example is this one from Jundee gold deposit, where we have a sample, and if we want to take a more detailed look in terms of, say, laser ablation ICP-MS on the sulfides, you can see a lot of pyrite through there, and they're shown up nicely in green. We may only be able to do a handful of these pyrites. So which ones do we choose? And on the face of it, they all kind of look the same. But when we look in detail, and this is just that area showing the pyrites now, arsenic is in red, nickel's in green, and cobalt is in blue. We can actually see that the pyrites show a whole range of different compositions and different zoning morphologies. With some have cobalt-rich cores, some have nickel-rich cores, and arsenic-rich overgrowths. And so if we want to really pull apart the trace elements with a technique like LAICP-MS, using this kind of larger scale technique will really allow us to resolve that. And I was quite pleased when I looked at this. This is the spectrum here. Cobalt has a rather nasty overlap with the iron, and we're actually seeing the cobalt shoulder in this spectrum here. So the deconvolution is working, the cobalt is real. So just to kind of sum up, we've got a whole range of different techniques that are available to us now, as was nicely illustrated this morning, and we can start producing new methods to objectively analyze these. The core scale XRF mapping allows us to connect the larger scale core and deposit scale data with the more kind of niche research infrastructure, which is very powerful to answer these questions, and that there's a whole range of opportunities in terms of exploration and also ore body knowledge kind of going further downstream. So I'll leave that one there. Thanks.